Welcome, my dear students. Let us continue the stereochemistry, optical isomerism. Okay. Now I will go to the topics types of optical isomers. Types of optical isomers. What are the different types of optical isomers? We have already discussed different types of what is optical activity, what are the optical isomers, what is the condition for showing optical activity. Now, optical isomers are classified as or differentiated as enantiomers, enantiomers, diastereomers, diastereomers, then mesocompounds, I just write like this, DL pair, or this is also called a racemic mixture. Racemic mixture. These are same. Okay, we will discuss one by one. Enantiomers, diastereomers, mesocompound, DL pair, racemic mixture. Okay. For time being, let us take one example, that is lactic acid. Lactic acid. Lactic acid is CH3, CH, OH, COOH. That is 2-hydroxy butanoic acid. Sorry, propanoic acid. Propanoic acid. And this carbon is optically active. Okay. This carbon is chiral carbon, therefore lactic acid is a optically active molecule. Now let us discuss what is enantiomers. Enantiomers. Okay, fine. Let us discuss what is enantiomers. 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 Enantiomers are optical isomers. Enantiomers are optical isomers, having same molecular formula, structural formula, and chemical properties, but behave differently towards plane polarized light. Next point, enantiomers are, this is very important, enantiomers are mirror images each other. Mirror images each other. They are mirror images each other. This is the most important point. They are mirror images each other. Let us take the lactic acid. Suppose lactic acid is like this. H CH3 COOH OH. Suppose this is lactic acid. Now from I draw a mirror here. Suppose this is a mirror. How will be the image of this molecule reflect in the mirror? What will be the image of this molecule in reflect in the mirror? Imagine this is a mirror. Therefore, in the mirror, you will have a cross like this, and in the mirror, OH will be here. You just see this is a mirror. OH will be here, CH3 will be here, H will be here, COH will be here. These two are the enantiomers because they are mirror images each other. And this mirror image is this mirror image is non-superimposable. Non-superimposable. This is okay because when mirror images are non-superimposable, then only they become optically active. Therefore, enantiomers are mirror images each other, and the mirrors are not, the images are non-superimposable. Suppose I pluck the molecule, I take the molecule and bring like this, non-superimposable, because I pluck and bring like this OH will come here, CH3 will come here. Therefore, they are not non-superimposable. Now, let us check it. If you give R and S nomenclature 1, 2, 3, 4, this is R because fourth group is on the vertical line. This 1, 2, 3, this is S. Therefore, enantiomers are like this. Enantiomers are like this. Very, very important. Enantiomers are like this. R and S. R and S. That is, if molecule 1 is R, the enantiomeric pair will be S. If it is S, it will be R. Okay. That's how enantiomer is working out. Okay. Now suppose you have two chiral centers, R and R, S and S. S and S, R and R. R, S, S, R. Where is R? There should be S. Where is S? There should be R. S, R, R, S. These all are enantiomers. Okay. Okay. We will take another example for enantiomers. Okay. We'll take another example for enantiomers. Students, now let us discuss another kind of molecules where more than one chiral centers are present. What are their enantiomers? I said to you, if there are more than one chiral centers, if first chiral center R, second chiral center S, or first chiral center R, second chiral center also R, or first chiral center S, second also S, S R, its enantiomer is SR. This one is the SS, this is RR, this RS. This is an enantiomer of this one. Okay. These are the enantiomers. These are the enantiomers. These are the enantiomers. This is the enantiomer. Okay, let us check it. Anyway, enantiomers are mirror images each other. Suppose this is the mirror. Therefore, how could be its image? There will be a square like this. The image will be like this. OH here, H will be here. Nothing changing. OH, OH, COOH, COOH. Okay, fine, students. Now let us find out the nomenclature, R and S nomenclature. 1, 2, this is 3. This is COOO, this is COHC. Therefore, this is 3. This is 4. It will be like this: 1, 2, 2 to 3. This is S, but R because H is not on vertical. Here 1, 2, 3. It is also like this. Fine, like this. S, but H is not vertical, therefore it is also R. Now let us come here. 1, 2, 3. 1, 2, 2, 3. This is R. This is clockwise R, but H is not vertical, therefore it is S. 1, 2, 3. Therefore it is also R, but H is not vertical, therefore it is also S. Therefore, in the position of R, in the mirror image it is S. Look at here. R become S. Here also R become S. Therefore, this is the example for this one. Therefore, these two are also enantiomers. You don't want to check like this. Don't want to check like this. If you just draw the mirror images, that's okay. But in the IIT JAM questions, they will give different formats. Therefore, this type of checking will help you to find out which is enantiomers. Okay. Now, okay, anyway, let us go to another kind of optical isomers, diastereomers. Diastereomers. What is diastereomers? Diastereomers. These are optical isomers. These are optical isomers. These are optical isomers. Same molecular formula and structural formula, but are not mirror images each other. But are not mirror images each other. They are not mirror image. They have same molecular formula, same structure, but not mirror images each other. They are not mirror images. Okay. That's all the optical diastereomers. That is, I will tell you, suppose it is RS, it will be RR. If it should be SR, it should be. Okay, they are like this. Now, I will tell you SS, it can be SR like that, or RR, it can be RS, or anything like that. They are not mirror images each other. That's called the diastereomers. Okay. I will tell you one example. Look at here. We can take tartaric acid again. COH, HOH, OH, HCOH. I take another tartaric acid, same molecular formula, same structure, but COH here, COOH here, here HOH, here also HOH. Okay. These two are diastereomers because they are not mirror images. This is not mirror images. Not mirror images. They are not mirror images. Anyway, let us take 1, 2, 3. This is S because clockwise H is not vertical. Therefore, they are S. H should be the vertical. We have discussed in Fisher projection discussion. R&S nomenclature. Okay. Now 1, 2, 3 come like this. This is also S. Now when you come here 1, 2, 3, you are getting like this. What is this? This is anticlockwise S, but it is R because H is not vertical. Now 1, 2, 3. 1, 2, 3. This is clockwise, but S because H is not vertical. Therefore, SS in the position of S you are R, but in this position of S you are S. Therefore, this is diastereomer. If it would have been R, the structure will be enantiomers. Therefore, this is not enantiomer, but diastereomers. Okay. Now, I will tell you one more important point. Actually, this is not the point concerned with optical isomers, but in stereoisomers, all geometrical isomers are diastereomers. All geometrical isomers are diastereomers. Students, diastereomers. That is cis trans, EZ, syn anti-type, also diastereomers. They are also diastereomers. Suppose I will tell you. Suppose you have CH3 here, CH3 here, H here, H here. This is cis. What is a diastereomeric pair? C double bond C, CH3, CH3, H, H trans. Therefore, these two are diastereomers. These two are diastereomers. Okay. Okay. Now, mesocomparts. Next one is mesocompart. What are mesocomparts? Mesocomparts. Mesocomparts are these are compounds containing more than one chiral centers, but optically inactive due to the presence of plane of symmetry. They are optically inactive due to the presence of plane of symmetry. They have more than one chiral centers, but they are optically inactive due to plane of symmetry. These molecules are symmetrical. These are symmetrical molecules. Their optical inactivity, their optical inactivity due to internal compensation. Their optical inactivity due to internal compensation. Let us take one example, mesotartaric acid. Mesotartaric acid. You take the tartaric acid like this, COOH. Okay, I just draw here for convenience. One example is mesotartaric acid. Example is mesotartaric acid. What is a mesotartaric acid? COOH, HOH. If you look at here, you have chiral centers two. This is one chiral center, this is also chiral center. But the problem with the molecule is, if you cut the molecule like this, these half are equal. They have a plane of symmetry. Look at here. If you cut the molecule here, you get identical halves. This half is mirror image of this half. Am I correct? Suppose you keep a mirror here. This half is mirror image of this half, or this half is mirror image of this half. Or you can cut into identical halves. Therefore, mesotartaric acid is optically inactive. But I tell you, it is due to internal compensation. What is the meaning of internal compensation? I will tell you. If I take R&S nomenclature, this is 1, this is 2, this is 3. 1 to 2, 3, this is anti-clockwise rotation, but it is R because hydrogen on horizontal, not on vertical. Now here 1, 2, 3, this is clockwise rotation, but it is S because hydrogen on horizontal, not vertical. Therefore, what is the meaning? These groups are same. Suppose the light has been rotated by clockwise in this is original position, in 30 degree plus 30 degree. But this half rotate the light, this half rotate in plus 30 degree, but this half rotate again into this direction. Imagine it was like this, into this anti-clockwise minus 30. Now after two rotation, our light is nothing but like this. Light is like this. Because light entered, this is the light entered to this molecule, this half rotate plus 30 degree, but this half of same molecule rotate minus 30 degree. After all this rotation process, the light leave back like this. Therefore, the observer see this light. This light which left to the molecule is exactly equal to the light which entered. Therefore, initial light and final light are exactly equal. Therefore, observer says that there is no rotation. The molecule is optically inactive. But that's not true, because the molecule has the chiral center. Because of that chiral center, there is a rotation happen within the molecule, but that has been compensated. That compensation is called internal compensation. Therefore, mesocompounds are optically inactive due to internal compensation. This is all about the mesocompound. Okay. Now I can go to next molecule. That is DL pair or racemic pair. DL or racemic pair. DL pair or racemic mixture. So pair or mixture. This is also called a mixture. It is the equimolar, that is equal moles, equimolar mixture of two enantiomers. Equimolar mixture of two enantiomers. This mixture is optically inactive due to external compensation. They can be separated into enantiomers by different methods. Okay, by different methods. They can be separated by different methods. They are optically inactive due to external compensation. Again, well, let us take lactic acid. Lactic acid, H, COOH, OH, CH3. What is its enantiomer? This is the enantiomer because they are mirror images. Very easy to take the enantiomers. Just draw the mirror image. You imagine a mirror here. Now you take this 1 mole, this also 1 mole, and mix them in a solution. This is 1, 2, 3. This is nothing but R. 1, 2, 3. This is S. This is R. This is S. You take 1 mole. Into a solution, you take 2 mole, 1 mole each, 1 mole this, 1 mole this. Now you pass a plain polarized light PPL to this, you will get exactly like this. Why? Because 1 mole of this rotate into this direction. Imagine it was our plane ball, this direction. This second mole of this rotate this molecule back and you will get original molecule. Therefore, it rotates back. Suppose this is R, this is S. Therefore, after the complete rotations, you will get exactly same plane polarized light. This is external compensation because that happened out of another molecule. In the internal compensation, both rotation happened within the molecule, but in external compensation, one kind of rotation is done by one type of molecule, opposite rotation done by another type of the molecule. But in internal compensation, that was not the case. Both rotations, first rotation and opposite rotation, were done within one molecule. Okay, that is why this is called external compensation. Okay, now I just draw all the structures of the tartaric acid here. Tartaric acid, you have draw the structure of tartaric acid is usual questions. We have tartaric acid. This is or HH. It's look like mirror image. I agree. It's look like mirror image, but both have a planar symmetry. Therefore, suppose you put A and B are Mesocomparts. Okay. Now you draw OH here, H here, H here, OH here, COOH, OH, H, H, OH, COOH, COOH. Where C, this is C and D. C and D are enantiomers. Because they are mirror images, they have no plane of symmetry. Okay. Now you just draw COOH, COOH, H, OH, HOH, E. C and E or D and E are D and E are diastereomers. These two are diastereomers. This is all about the tartaric acid. More examples you can do. Okay, thank you.